In this lecture, we are going to talk about the synthesis and reactivities of pyridine, quinoline, and isoquinoline. In the first lecture, we will talk about the synthesis of pyridine. Pyridine is used as solvents and bases in many organic reactions. It is miscible with water, and it has been first isolated from bone pyrolysates and coal tar, but for the first commercial production was prepared in 60 to 70% yields by the gas phase high temperature interaction between acetaldehyde, formaldehyde, steam, air, and ammonia over silica alumina catalyst. So the reaction occurs by cross-outdoor condensation with to form acrylane, and then reacting with the ammonia to form pyridine analogs. Pyridine is an important unit for bioactive molecules. For example, for nicotine containing a pyridine ring, it is found as an active ingredient in tobacco. It is toxic and addictive. And paraquat is the pyridinium salt. It's one of the oldest herbicides, although it's very toxic and non-selective. Last one is the sulfapyridine. It's an antibacterial agent of the oldest kind, containing a pyridine ring in its core molecule. There are many drugs that contain pyridine in the market. For example, Nexium having a pyridine as a core structure with 4 substituents. Actos from Eli Lilly is the type 2 diabetes drug, has a pyridine with 2 substituents. And Gleevec from Novartis is the drug for leukemia disease, having a pyridine and pyridine in a molecule. In order to synthesize those pyridine-containing drugs, you need to learn how can you construct pyridine ring. So the first ring synthesis of pyridine is probably the simplest. Is the condensation between 1,5-dicarbonyl compounds with ammonia. So if you have an unsaturated 1,5-dicarbonyl compound, as we talked about this in the second lecture, that the ammonia can attack and once to form the enamine, and the enamine can attack again at the another carbonyl groups to form another enamine. So your final product is not the pyridine yet. You will form kind of like the double enamine unit here. So from here, you need to oxidize the hydrogen by using some of the oxidizing agents, but they are easily dehydrogenated to pyridine because pyridine is stable. Another alternative way to synthesize is to use 1,5-dicarbonyl compound that already contain one double bond in the molecule. So from here, if you react with the ammonia, this can lead directly to the pyridine ring because you already have one double bond. So you can see that if we have the 1,5-dicarbonyl compounds, it can be easily converted into a pyridine ring by condensation with ammonia and then oxidation. However, the difficult part is how to synthesize the 1,5-dicarbonyl compound itself. And if you do the simple disconnection here, you can see that it can be generated from the nucleophilic attack of enolate through the microaddition to the alpha-beta unsaturated carbonyl compounds. So because these two compounds are commercially available, it's easily prepared more than the 1,5-diketones. So now you can synthesize the 1,5-dicarbonyl compounds and hence the pyridine itself. So if you look at this following example, This one doesn't have the one alpha beta unsaturated ketone because maybe from this molecule it is not very stable. It is usually easily polymerized, so we use something that as a mask. So you can see there is a leaving group here, and under high temperature this one can undergo elimination, and then you can generate the alpha beta unsaturated ketone, and now the ketone can tautomerize to form the enol, and this can undergo nucleophilic attack microaddition, and at the end you are going to get the 1,5-dicarbonyl ketone here. So from here, if you add ammonia, you will condense to form the dienamine type, and then after that you need to oxidize the ring. Maybe the nitric acid is good enough as an oxidant to generate the pyridine of your choice. So if you want to avoid this oxidation step, instead of using ammonia, it is probably easier to use the hydroxylamine here, because the dienamine type that you got will have an already installed a leaving group of OH. So if you heat it up, you can eliminate water and then generating the pyridine that like in one step, no need to oxidize further. In the next example, there is no alpha beta unsaturated carbonyl compound, but you have the ketone that can react with DMF, DMA, which has structure like this. There are two leaving groups in the molecule, and under basic conditions and heat, it can eliminate and then forms the intermediate like iminium salt. And under basic conditions, some of the ketones got deprotonated using potassium hydroxide, and now you are going to form the enolate of ketone, and this enolate can attack the intermediate. And after elimination of methanol, it will lead you to this intermediate, which is actually the alpha beta unsaturated ketone, and another molecule of enolate can comes in and attacking here, to form a new carbon-carbon bond here. And now the good part here is that you already have another leaving group here, so you can kick out the amine as a leaving group, and from here you can form the leaving form one double bond in the 1,5-dicarbonyl system, so that when you put in ammonia, it will generate the pyridine like straight away. And if you look at the structure here, there are 3 pyridines pointing nitrogen inside, so this compound is useful as a ligand as well in transition metal chemistry. Another way to generate 1,5-dicarbonyl ketones is by doing the ozonolysis reactions of one of the cyclopentene. So the ozonolysis will cleave the double bond here, and then you are going to get the 1,5-diketones precursor that you can use to form the pyridine. Apart from using 1,5-dicarbonyl ketones, another popular reaction for formation of pyridine is to use an aldehyde here with two equivalents of 1,3-dicarbonyl compounds. So here and here. And also you need one equivalent of ammonia as well. So this will construct a the almost pyridine-like structure that can be oxidized easily to form the pyridine. And the process is well known as Hansch synthesis. So you have 4 components in one reaction. If both sides are symmetrical, you can do everything in one step. Like in here, the ammonia can attack here, and then the enamines attack here, and then this also attack here to form the enamine that attack here. So you can try to draw out the mechanisms by yourself. And after formation of this Hansch ester, the intermediate here, it can be easily oxidized by, for example, sodium nitrite to generate the pyridine. However, for the unsymmetrical pyridine, you need to separate the 2 steps. So in the first step, you may react the 1,3-dicarbonyl compounds with aldehyde first. The reason why it needs to be the 1,3-dicarbonyl compounds because this compound is more likely to form the stable enolate that can cleanly attack the aldehyde. So the 1,3-dicarbonyl compound is a good source of nucleophile that can be used. So here, this carbon as a nucleophile, this carbon as an electrophile. If you draw the enolate, this can attack here to form the new aldol product here. And the second part, you may synthesize this from the 1,3-dicarbonyl compound as well. So with this molecule, if you put ammonia, the ammonia can attack the more reactive ketone and then forming the enamine. And from here, the enamine can use carbon here as a nucleophile to attack carbon here, and it can use nitrogen here as a nucleophile to attack the carbonyl group here. So you can try to draw out the mechanisms by yourself. Okay, and from here, if you heat the reaction up, this will eliminate water and hence forming the intermediate, and you can easily convert this to pyridine by oxidation. Actually, you don't need the second carbonyl group if you do it step by step. For example, here, if you put the ketone with base, the only enolizable part is the is this carbon, because that's the only alpha proton. And from here, this will attack the more electrophilic aldehyde. And after elimination at reflux, you are going to form the aldol product here. With a new CC double bond, and hence you are going to generate the alpha beta unsaturated carbonyl compound. And the other molecule of the ketone, so if you deprotonate here, it's become the enolate, and this can attack. Under BF3, this can act as a Lewis acid to activate the ketone to be more electrophilic. And after forming the 1,5-dicarbonyl ketone, then you can use ammonia to condense and forms the pyridine ring here.